avoid machine learning, at least today. Not anymore. Sorry. So first of all, some credit. This is the work of Abdul, who's done all of this for his PhD. He's now about to submit very soon. Early August, so Colin gets enough time to read it and write the report. Thank you very much for doing that. And then Sebastian is the co-supervisor for this. If you want to read up, Abdul has published 2 very nice papers which you can read basically about almost everything I'm saying today. So Parareal, I don't really have to say a lot about. I guess everybody here has seen Parareal a few times. I think we've even seen this picture here already. So the idea is, right, you want to solve an initial value problem. You split your time interval into what's typically called time slices, so 5 here in this case. And then you find a good time stepping method which satisfies all of your needs, is stable, is accurate, however you want it. This is called the fine propagator. And then, like the classic serial thing would just be you go through this with your fine propagator, then here, then here, then here, then there. And of course, this is a horribly serial procedure. So if you want to actually introduce some form of concurrency, you have to come up with a clever trick, because typically you're going to know the solution here before you can compute anything here. And this is what Parareal does. It asks you to somehow come up with this G, which is a coarse propagator, and then you replace this serial fine propagator by this iteration. So the idea is you run through the whole thing with the coarse propagator. This gives you a rough idea of the solution at the beginnings of these time slices. Then you run your expensive fine method on all these time slices in parallel. Well, then, of course, you have an error here because you've started from the wrong initial value. So you iterate and you correct. And if you look really hard at this iteration, K is your iteration counter, N is the index which indexes your time slices. You see there's a serial dependency. You have to compute the VK plus 1 in the current iteration at this point before you can compute the VK plus 1N plus 1 solution at this point. So this update here in the G has to be done in serial. And it's probably not surprising, right? I mean, time propagation and information in time propagates serially from the beginning to the end. At some point, this has to be reflected. But this also means that the performance of Parareal, and I guess a lot of other parallel time methods, really rises and falls with what you do for the G. Right? This is where all the magic is. And for Parareal, this is actually quite nice. You can see this. You can come up with a relatively simple model for the kind of the best case speed up you could get from Parareal. It looks kind of like this. So best case just means we assume we have a perfect computer. There's no overhead, no load imbalancing, all the kind of things you would see in a real application. But we neglect all of this and just look at the best case. And then you have this expression. You have K is the number of iterations you need to converge. How often do you have to switch between fine and coarse propagators? This is the number of time slices or processes in time. And then you have this ratio. So this is how long does it take to evaluate one coarse propagator divided by how long does it take to evaluate the fine propagator. And then you can stare at this a little bit, and then you can quickly convince yourself that this must be smaller than the smaller of these 2 bounds. And the first bound is the time for the fine divided by the coarse propagator and the number of time slices divided by the number of iterations. And now these 2 bounds are in conflict in that, I mean, on the one hand, you could basically choose the fine propagator to call the coarse propagator to just be the fine propagator, right? You converge in 1 iteration. So you're really great, doing really great here. But of course, in this case, this ratio is going to be C fine over C fine. So 1, so you're never going to see speed up, right? So that's useless. The other thing you could do, and we actually learned that this isn't always a bad idea if you just use no coarse propagator.
Parabolic and Dirichlet conditions. Yeah.
So in most cases, though, if you did that, this bound here, like your coarse propagator is basically runtime 0. So you've got no limit from this bound. But in most cases, your K is going to be fairly large and probably close to your P time. And then this bound is going to be very, very bad, unless you are in a very specific setup. So somewhere, what this means is somewhere in between there's something like the optimal accuracy for your coarse propagator, where you're still very cheap, or still cheap enough to make this bound good, but still accurate enough so that this bound doesn't do you in. And this was just, I don't know, I just played with this. The problem is, of course, that typically there's some relationship between the C coarse and the K that we don't know. And I just wanted to play with this, so I just came up with some formula to connect the two, which is absolutely disconnected from reality, in that I didn't do any actual tests. I just came up with a nice formula, which basically the idea here is your coarse propagator, which does nothing. And I just assumed, even now I learned today, this isn't necessarily true, that if your coarse propagator does nothing, you need as many iterations as you have time slices. And then all the way here, this is where your coarse and fine propagator are identical. And I just came up with a formula that basically interpolates between this, like 1 minus coarse to the power of 4 times p minus 1 plus 1. And then you get, this is the number of iterations you need. And then this is the speed up you get. And you very nicely see, like here would be the best scenario. The power of 4 here, this is actually interesting. At first, I didn't have a power. I just saw the linear term. And then the speed up was always smaller than 1. And I thought I did something wrong. And after a while, I convinced myself, no, it's just that if your number of iterations doesn't decay quickly enough, in a sense here, as you make the coarse propagator more expensive, you just don't get any speed up. Yeah. So
With the example from this morning I had with the reduced basis, we could actually calculate this curve.
Yeah.
We could calculate this precisely, right?
Yeah.
Having the precise decay, you have the precise cost.
This would actually be, this is
We should do this.
what I thought. It's like you could plug actually some more realistic connection in here and actually come up with an actual performance model where you're not choosing this and this independently, but
it's exactly, yeah, for my example, I have the numbers.
yeah,
It's pretty good.
look at this. All right, so now this is, of course, where machine learning comes and rides to the rescue, maybe. So this is just for fun. So TUHH, we have an interface to ChatGPT, which is called TUKI. So TU for Technical University and KI for Künstliche Intelligenz or AI. My wife gendered TUKI as female, so I always refer to TUKI as she. I don't know why, but it has stuck. TUKI is really nice. She's very friendly. You can talk to her. Sometimes she's actually extremely useful, but when I asked her to summarize the state of the art for solving PDEs with machine learning, well, okay, I mean, there's like, it's not wrong, but it's also not terribly insightful if you know already a little bit. So there's pins, everybody knows pins. It's like the standard approach for solving PDEs, flexible mesh-free approach. But there's some evidence. So there's actually an increasing amount of literature where people actually try and solve differential equations with machine learning. And sometimes even with good results. So this is from the paper here, where this is essentially they learn LU factorization. So it's just solving a linear system. And they compare this against a couple of numerical solvers, which is already great, right? I mean, this is what you should do. If you want to do machine learning, replace numerical solvers, please at least compare against numerical solvers. Lesson 1. So they did this. And you can see like the red line is their deep neural network. And this is the size of the equation. This is the solving time. And they actually took some care to make sure this gives comparable accuracy. And you can see that in certain regimes, the neural network actually can win. And then they went and solved the heat equation, but they did no longer compare against the numerical solver. I don't know why. Yeah, but so it's not completely insane to look at machine learning techniques to try and solve differential equations.
Well, this was a dense factorization.
Yeah, this is a dense problem.
It finds Strassens algorithm or something. What did this find?
Actually, I don't know. I have to look it up.
Yeah, NumPy will choose depending on the size of the.
Yeah. But no, this is like the LU package, and I think there's some Fortran package behind it which does
Usual LA package.
Some better, yeah.
But I mean, at least this is a fairly state-of-the-art numerical solver. Okay, so they're not. This is, I would argue, a reasonably fair comparison in that whatever is in NumPy LU is probably a fairly decent numerical implementation of a good algorithm.
But it's not known what the machine learning thing found. It's not known what the machine learning thing found as a technique.
Comparable error, I think is what you said, right?
Yeah,
No,
they
but what
did.
structure, what's the mathematical technique to solve that?
Oh,
A2 norm, that's good.
yeah. I mean, they probably looked at L2 norm. I don't.
I think, did it find a better LU? Did it find, what did it find?
Pointing out that it scales better than any of the classical algorithms.
Yeah, exactly. So what
So how-
factorization did
what
it find?
algorithm did it find? Yeah, that's the goal.
That's what I want to know.
Is LU equal to A?
To be honest, I don't know. I don't think they looked at if this is reproduced any of the algorithms. It just does its magic, produces an answer. And here it happens to give a reasonable answer in sometimes faster time.
Well, the slope on that line is different.
Very different.
That's
Something's fishy, no?
It's probably because it's saying what is the probable solution to the L.
an artist rendering of the solution.
Yeah.
Right. So what we wanted to do is we didn't just want to replace numerics with ML, but the idea was to use ML as a component of the Parareal algorithm. So the idea is your fine propagator remains your trusted numerical method, which you understand, where you know what it's doing. Or maybe we can replace the coarse propagator, because there, I mean, in the end, the coarse propagator is just a tool, right? As long as Parareal converges, we don't really care so much what it does. If it's so, and we use the Black-Scholes equation. This is computational finance. I really don't know anything about it, but Abdul, when he started his PhD, said he's interested in computational finance. I told him, well, I don't know anything about it, but we can definitely pick a PDE that has applications in this area. So it's like basically what X and Y here is not physical dimensions, but it's you have like a portfolio of two assets, and X and Y is the value of your assets, and then this gives you the total value of your portfolio. But I have to admit, I never really understood how this worked. But finance people use this equation, probably in higher dimensions, but it's not like, you can see, right? This appeared in a proper economy journal, right? So anyway, for us, this was interesting as an example for a PDE, which is reasonably complex in that you can see it's like a time-dependent partial differential equation. This here is kind of like a heat equation part where the coefficients, so what in a physical heat equation would be your thermal diffusivity, depends on your X and Y coordinates. So it's kind of quasi-linear, right? And then you have these sigmas here, which are volatilities. And then you have this mixed derivative here, and you have this, what I would call kind of advection terms, again, with the X and Y dependent speed and this parameter R. And you also have like a reaction term. So it's like, it's an interesting PDE. It's got all of the things you want. There's diffusion, good for Parareal. You've got advection. So if you make the R really small, you move into something like an advective dominated regime. You have a mixed derivative. So there's something happening. It's not a trivial example. And so the approach we did is we used Fourier neural operators, or physics-informed neural operators. So we didn't use pins, physics-informed neural networks. This is probably the most widely studied approach for solving differential equations. We haven't had that much luck. In the first paper, we took a pin architecture and we bend it to kind of do what we need in Parareal. So in Parareal, I mean, essentially what your coarse propagator does is you stick in the solution at a time t, and you want it to return the solution at ut plus delta t, where this is the length of your time slice. This isn't really what pins are made for, but we kind of twisted it into a way that it did what we needed, and it actually worked reasonably well. But then in the second paper, we actually looked at the neural operators, and it was just throughout the board a lot better. I'm going to show a bit of comparison later. So the idea in neural operators is essentially you're not learning the solution, you're learning a mapping. And in most of the papers, it's like you learn a mapping from some parameter in your solution. Like for example, in the Black-Scholes, you could try and learn the mapping that for a given volatility produces a solution. Or a very frequently studied problem is of Darcy flow, where you have some diffusivity, and then you map from the parameters in your Laplacian to the solution. So this kind of operator is what the neural operator tries to learn. but you can, it didn't really take a lot of work to make this learn this mapping, right? Where what you stick in, the input is basically the solution at the beginning of the time slice, and what your neural operator produces is this solution at the end of the time slice. Yeah? So there's a code in the paper. This is the paper where they introduced this, and there's a code on GitHub. And I don't think it didn't require a lot of modification on upload side. It was really not very difficult to bring this into the form that we needed. Very roughly how it works is like, it has this combination of some stuff it does in Fourier space and some stuff it does in physical space, which I think is what makes these neural operators work reasonably well. So it's essentially you have this is like you stick in the function in physical space, it gets transformed into Fourier space, then it learns, like this is what the neural network does, it learns the propagator in Fourier space, and then it transforms back and gives you the output. But there's also connections which don't go through Fourier space, but where it's actually directly learning this operator in physical space. And the advantage is that the Fourier modes tend to be doing very well for the larger scale features, but then this W, the one that stays in physical space, also allows the network to learn something about the small scale features which are not very well represented in the spectrum. Yeah, and so our experience with these architectures has broadly been quite positive. So they seem to be relatively good.
It's all in one architecture. Do you have to split the equation for this quick and slow part, or for this?
No. This is the architecture.
One architecture you have.
just stick this in and it does it by itself.
Okay.
Okay. So here are the results. So what we did is we took the neural operator, we used physics loss. It's like we basically put the partial differential equation into the loss function and used this for training. And this worked actually quite well. So this is the loss function. So essentially these are three types of loss. The residual loss is the PD, boundary loss is the boundary condition, and expiration loss is, the equation is a bit odd in that it has a final condition, not an initial condition, but yeah, so you prescribe a final condition. And you see all of these, like you encode in the loss function, you train, and the training does reasonably well. You go from 10 to the 3 to 10 to the -2. So that's good. And what you get is, so this is what I said, this is our first attempt where we use the modified pin. And then this is a physics-informed neural network. And you see like the pin required a lot more trainable parameters. So this is 1.2 million worth of 830,000. The training time for the pin was 42 minutes, whereas for the Pino it was just 10 minutes. And the accuracy for the Pino is also better. So we didn't really see any reason to stick with the pin. The Pino architecture was just winning across the board. And then this gives you, an accuracy of about 1%. And in comparison, the numerical propagator, which we built for the system based on an implicit Euler and a finite difference discretization, gives you an order of about 2%. So it's very comparable in terms of accuracy. But in terms of runtime, so this is a fully serial fine propagator. This is just numerical, right? This takes about 350 seconds. And this is standard deviation. So we did 10 runs on average, but you see its standard deviations are very small. So the runtimes actually, yeah.
What's the discretization on the fine?
It's a second order finite difference with a trapezoidal rule, I think. So second order space and time, right? So it's a two-dimensional problem. So it's already reasonably big. The resolution is relatively high. So we've got about 2 times 10 to the -3 accuracy on the fine propagator. And you see, like, this is if you parallelize the fine propagator in space, right? You eventually can bring this down to 37 seconds. This is basically where the space parallel scaling saturates. This is your numerical coarse propagator. So this is 113 seconds. And the Pino brings us down to 2.2 seconds once trained. So this is enormous, right? This makes your coarse propagator about 51 times faster while maintaining comparable accuracy. That's actually really good. And even in terms of training times, right? I mean, here, it took 10 minutes to train the Pino, which is about 273 evaluations of the Pino, or about 5.3 evaluations of the numerical G. So this isn't insane. It's not like, I mean, obviously you have an overhead here from the training, but it's not like you have to do 1 million evaluations of your coarse propagator to offset this. And if you're thinking something like a setup of optimization, model-based control, where you actually have this multi-query setup where you're going to solve your differential equations a couple of times, offsetting this factor of 5 is probably going to be relatively easy. Yeah. And again, you see like the pin, there's really no reason to use it. It's also much faster than the numerical coarse propagator, but it's slower than the P0. Right, what does this give you in Parareal? So here's now the experiments for Parareal with the different propagators. This is convergence. So this is the error against iterations. And you see there's really not much difference. It doesn't matter. You can use a numerical coarse propagator, you can use a pin, you can use a P0, they all converge almost exactly the same. Yeah. One thing that was interesting, one of the reviewers suggested we try this, is basically if you use a P0 and you stop the training early, right? So after 500 epochs, 1,500 or 2,500 epochs, yeah, I thought this is quite interesting because what happens is if you stop the training too early, you get very similar convergence behavior, but everything is just shifted up, right? You get higher errors. I don't know why. I thought this is interesting. So the behavior is the same, you just get higher errors. And then here 1,500 epochs is the best. And then after that, you get actually up again a little bit because probably of overfitting. But actually, I mean, this is relatively stable. And then here's speed up. This is speed up just from Parareal. All the way up to 64 cores. The gray line is a model for the Pinot Parareal. The dashed line is a model for the pin Parareal. The dotted line and the dashed line is for the numerical Parareal. And you see the numerical Parareal, because the coarse propagator is so expensive, you just don't get anything really. The pin is a lot better than the numerical, and then the Pinot is even better still. And the only reason is you keep the number of iterations constant because your accuracy and convergence is the same, but your coarse propagator is much, much faster, 51 times in this case. That's really nice. Then the question was, well, what happens if you parallelize in space first, right? Typically, you don't just want to use Parareal, you want to parallelize in space, and then use Parareal to parallelize on top of this. And the answer is, well, you maintain fairly good performance. So here, this is your pure space parallelization, scales up to 16 cores and then goes down again because of overheads. And with Parareal, with the Pinot Parareal, you can actually, like this is with 1 iteration, this is with 2. After 1 iteration, you're already about at the order of the discretization error of the fine method. Here, you're well below. So this is definitely justified, 2 iterations. And you see, like this is the best you can do with space parallelization. It's about 16. And you can bring this to, well, I don't know where this is, about 25. This is almost a factor 2 additional speed up from Parareal. But you can only do this with the machine learning based coarse propagator. The numerical coarse propagator never gets actually, like never manages to beat the pure space parallelization simply because the coarse propagator is too expensive. Then, of course, one question we've already discussed, does this generalize, right? So what happens if you want to solve the same PDE, but now you have different parameters? And so this is like a generalization study. So we trained this for, these are just like volatilities, and this is the risk-free interest rate. These are just the 3 parameters in the equation. And we picked them kind of at random and trained for this. And then we changed the parameters in the fine propagator. And we used the Pinot without retraining it. So essentially, we used the coarse propagator that had been trained for the wrong parameters. And this is convergence. And you see, like, the red line is a trained value, and then we go from 1 to 5. This is the black line. And actually, because the bigger the R, the more
That's diffusive.
wait, no, so the smaller the R, the less diffusive the problem is. No, the other way around, sorry. This is why if you make the R really small, you actually get better, even though you move away from the trained regime. It's just the coarse propagator gets less accurate, but your problem becomes more diffusive, so in the end you win. But generally, it's not hugely sensitive, right? And here's with the change in volatilities. If you push this too far, right? So we've trained for 0.2. If you push this to 5, the black line, obviously, right? Eventually this stops. But it's not like it just works for the parameters you trained in. You can go relatively far and you still get decent convergence and would probably still see a reasonably speed up from the method.
Are the parameters inputs to the neural network, or is it just you're just taking it as a black box?
We're just taking it as a black box and just use it. I'm gonna skip this because I want to show these results, which are the ones we haven't published yet. So we wanted to kind of switch things around, and the idea was maybe we can machine learn a coarse propagator and then look at what it does, and maybe this can tell us something about how we build good coarse propagators.
That's the SVD of the map. Like
Mhm.
I did this.
Maybe, yeah. So what we did is we replaced the Pinot just by a dense neural network. We didn't use black skulls, just 1D advection. It's no physics loss. We basically just train it on the analytic solutions for different parameters. And we kind of use 3 different loss functions. The first is we just try to get the coarse as close to the fine in the L2 norm. The other is we're going to try and get parareal after 1 iteration. So you could use multiple, but we always used 1. Parareal after 1 iteration as close to the fine as possible. And then the third one, I'm actually not showing any results because this performs very similar to this one, is we do the same as here, but we also penalize deviations from the max from 1 because we don't want parareal to overshoot, right? We don't want parareal. I mean, we know for the advection equation, the amplitude should stay at 1, and we kind of want to penalize parareal if it overshoots, but it turns out this makes very little difference because it's kind of already inherent in here. And this is like, first of all, training, it's fine. Both of these variants train very similarly. And then here's a convergence. So the blue is a numerical coarse propagator, and as you know, advection, no convergence at all. The orange line is if you train the neural network to be as close to the fine propagator. And you see, if you just try to match the fine propagator, this doesn't really help. Yeah, errors are a bit slower, but it doesn't really converge. But if you train the neural network so that parareal after 1 iteration is as close as possible to the fine, it's still not great, but at least you start to see some contraction. I found this interesting because this means that getting your coarse propagator just as close as possible to the fine is maybe not the best idea. And then we also looked at what do these different coarse propagators do, and to be honest, I can't really make a lot of sense out of this picture. So the numeric coarse propagator is non-diffusive, which is bad. The neural network understands that it needs some diffusion, but basically, if you just match fine to coarse, it seems to diffuse too much. And if you use the fine minus parareal after 1 iteration, it seems to learn exactly the right amount of diffusion. But to be honest, I haven't really, I wouldn't claim that I really understand what's going on there. So if anybody has any good insights, please lay them on me. Where this is still work in progress, so we're still trying to make sense of what the neural network is actually trying to do. But maybe somebody else has some brilliant insights out of that. Well, anyway, thank you very much for listening. If you want to read the papers, here they are, and I'm very happy to take questions.